So I have a question for us to think about. We have a farmer, and he's acquired a certain amount of fencing, like 2,000 feet. And he needs to build a rectangular enclosure with this, and he wants to do it in such a way that it has the biggest area possible. So this is kind of a classic example of what's called an optimization problem. We've got a bunch of constraints, the amount of fencing, the dimensions, and so forth, and we want to find the biggest way possible to do something. So I'm going to apply just kind of the usual approach that I take to problem solving here. This is a physical problem, right? It's defining a physical object, this rectangular enclosure. So I'm going to start by drawing a picture. We have our rectangular area, and I'm going to label the dimensions because those are what we're trying to find, right? So I'm going to call these G and W. I'm going to use W for the width and G for the length. If you want to use an L there, that's fine. If I'm writing this on the board, for example, and I can do kind of an L with a loop, right, then I'll use an L. When I'm doing stuff here on the computer, there really aren't any fonts that have an L that doesn't potentially look like a 1. Right? So I usually try to avoid that as a variable, which is why I'm using a G here instead. So then the next thing I started thinking about is, what is this equation about? Right. Well, it's about the dimensions of these objects. Right. First, I want the biggest one possible. We measure big for a two-dimensional object with area. Right. So the area of this thing, it's a rectangle, so it's length times width, which is going to be W times G. And you need to keep really firmly in your mind, this is the thing I'm trying to maximize. Right. So what else do we know? Well, we also have information about essentially the perimeter, right? The distance around. That's going to add up to 2,000 feet. So let's write that. Right? The perimeter of a rectangle is 2 times the length plus 2 times the width, and that's going to have to equal 2,000. Now, when I see this, almost like reflex. We've got all those 2, so the first thing that comes into my head, I'm going to divide through by 2 just to make the numbers a little smaller. It's almost always going to make our life easier. So the equation becomes G plus W equals 1,000. All right, now I'm going to fall back on what we talked about in the last lecture. Right? We saw in the last lecture that if we have a situation where the sum of 2 variables is constant, their product, which is what that area is over there, their product is maximized when the 2 variables are equal to each other. Right? In this case, when W equals G equals 1,000 divided by 2, which is going to be 500 feet. So the answer ultimately is a square, right? A 500 by 500 foot square. So I've got another question here. This one is going to be a little more complicated. We have something called a Norman window. It looks like a rectangle with a semicircle on top. And I know that the perimeter has to be 20 feet. That's, again, the distance around. And I want to know what dimensions will emit the most light. Well, again, the biggest object is the one that's going to emit the most light, and we measure big by area. So ultimately, it's the area that I'm going to be focusing on here. So first, I'm going to start off with a window. Start off with a drawing of the window. And I'm going to label some of the dimensions here. Now I'm going to label this one H for height. And what about the next one? Look, I'm looking ahead. Okay? You might want to call the bottom one W for width, right? And yeah, okay, you could do that. But we've got that circle up there. And I know that there's no way we're going to get out of this without having to talk about circle formulas. And circle formulas, I'll use the radius. So if I put W down there for the width, then the radius is going to be W divided by 2, and now we got fractions in the process. To keep things a little simpler, I'm going to call this 2R, and the radius of that semicircle R. Okay, I think hopefully that's going to make things a little easier as we go along. Okay, now let's focus on the perimeter of this thing. Right, it has to be 20 feet, and you need to be careful. Right? Because remember, perimeter is just going around the outside, not necessarily every line in the drawing. That line that cuts across the middle there, at the top of the rectangle, bottom of the semicircle, that's not part of the perimeter. So the perimeter will be 2R, that's the bottom part. two h's, those are the two vertical parts, plus pi times r. Remember, 2 pi r is the circumference of a circle. We've only got half of one, so it's going to be pi times r. Okay, so how about the area? All right, well, the area has two parts. The area is 2r times h, that's length times width. That's how we find the area of a rectangle. And the area of that semicircle up there, well, the area of the full circle is pi r squared, which means the area of the semicircle is 1/2 pi r squared. Okay, none of the rules or theorems that we talked about in the last lecture are going to apply here. We don't have two variables. We don't have the sum of two variables equals a number, or the product of two variables equals a number. We've got some more complicated expressions. Okay, and that's fine. Sometimes we have to fall back and actually do the work ourselves. So what I'm going to do here is I'm going to solve the perimeter formula for h. I could solve it for r. If you wanted to do that, that'd be fine. But I'm looking ahead. I'm looking over that area formula. I'm going to have to substitute whatever I solve in here for the other variable. And if I solve this for r, then I'm going to have to put it in there and square it, and things are going to start to get a little messy. Right? So it never hurts to kind of look ahead at the next step before you start making your decisions. So if I solve this for h, I'm going to subtract 2r and pi r from both sides, then divide both sides by 2. Okay, now I'm going to do the substitution part. Now I'm going to substitute this into the area formula. Yeah, could have been nicer, but it's not that bad because I've got the 2 outside the parentheses and the 2 in the denominator. They're going to cancel, right? So I'm going to cancel those 2's. I'm going to distribute the r into the parentheses, and I'm going to end up with 20r minus 2r squared minus pi r squared plus 1/2 pi r squared. And I know it looks a little messy, and it is, but it's just a quadratic function, right? And we know how to find the maximum. Hopefully, it's going to be a maximum. We'll talk about that in a minute. Just using the vertex formula. Okay, so I am going to clean this up a little bit first. Minus pi r squared plus 1/2 pi r squared is 1/2 pi r squared. Is minus 1/2 pi r squared. And I'm going to put that and the minus 2r squared in front, move the 20r to the back, factor the r squared out. All right, so this becomes r squared times negative 2 minus 1/2 pi plus 20r. And yes, I left the minuses in there. You might have been tempted to bring it out. Don't do that. Right? I'm going to put this into the vertex formula, which means I need the values of a and b. Right? To get the value of a, all of the number parts have to be in the parentheses. Okay, so now we're ready to go to that formula. Remember, the vertex occurs when r, our variable in this case, is equal to negative b divided by 2a. So I'm going to take that formula. I'm going to put 20 in for b. I'm going to put negative 2 minus 1/2 pi in for r. In for b. And, okay, this is good. It may not look good, but this is good. The 2 and the 20 are going to reduce, so I'm going to end up with a 10 on top. And now I'm going to pull, no, I'm not going to do that. Better way to do this. Distribute the 2 into the parentheses. If we distribute the 2 into the parentheses, it's going to cancel the 2 in that fraction. Right? I was going in the wrong direction on that one. So we're going to distribute the 2, and we're going to bring out the minus. Now I'm going to bring out the minus because it's going to cancel with that minus that's out in front. And we're left with r equals 20 over 4 plus pi. And that's our answer for r. Now, we don't have the dimensions yet, right? We're not quite done. So the next step to get those dimensions would be to substitute that into the h formula. Now, some of you may not be looking forward to substituting that into the h formula, and I get it. You're going to have some fractions inside of fractions and common denominators, and too many minus signs for comfort. It's going to be a messy business. So here's what I'm going to do. I always tell my students, look, there's nothing wrong with fractions. Nothing wrong with a fraction for an answer, but I tell them there are 3 situations when it's okay to go to decimals. Right? One of them is when the original question uses decimals, because your answer should always be in the same format as the original question's values. The second time is when you're graphing, because decimals are a whole lot easier to graph than fractions. And the third one is when you're answering a practical question, and that's really what we have here, right? This is ultimately a practical problem. You do not want to go to the shop foreman who's probably 50 years old and has been doing this since he was a teenager, and tell him that the radius of this thing he needs to build needs to be 20 over 4 plus pi feet. That's not a conversation that's going to go well for you. Okay, perfectly okay at this point to take that and turn it into a decimal. You notice that I doubled it, right? I did 2r because the bottom dimension there, the length, is 2 times r, so that came out to 5.6. And if I substitute that into the h formula, get your calculator out, whole lot simpler to do, we get h equals 2.8. Now when I saw this, I immediately stopped and I said, okay, wow, wait a minute. That's an interesting result. Because if 2r is approximately 5.6, then r is approximately half that. R is approximately 2.8 feet. And when I saw this, I said to him, did they really come out the same? Wouldn't that be interesting? Because that's what we saw in the previous lecture, right? A lot of the time with these optimization problems, the two parts came out to being the same. And turns out, at this point, I sucked it up and went and put 40 over 4 plus pi in there and did the arithmetic. I encourage you to do that as well, right? Convince yourself. If you do that, then yeah, sure enough, both the radius and the height are equal at 20 over 4 plus pi feet. Now, I need to issue a caveat here. It is not always going to be the case that they come out the same. Obviously, that happens quite a bit, right? It's not a result that we should be surprised by, but it's definitely not a result that I would expect to see or assume that I'm going to see.